This podcast is sponsored by the Building Performance Workshop, helping pros make more money doing better work for happier clients with advanced NBPI trainings and our new book, Home Performance Diagnostics. More at buildingperformanceworkshop.com. Enjoy. Welcome to the Building Performance Podcast from Green Dream Group in Chicago. I'm Corbett Lunsford. Today we're talking about trends in high-performance building and retrofits with Paul Raymer, who is the Chief Investigator of Heyoka Solutions and also the author of the book, Residential Ventilation Handbook. Paul, thank you so much for being on the program.
You're welcome, Corbett. Glad to be here.
So Paul is, in case you haven't heard his name, and you should have by now, he is a ventilation expert of the highest tier. So, Paul, what do you see happening in the world of ventilation and homes and buildings just here and anywhere you go and investigate?
Well, I think what's going on right now is, having been doing ventilation stuff for 30 plus years, I think the interest in mechanical ventilation now is higher than it's been in a long time. And the reasons for that probably are primarily the codes that are driving people to have to go there. I think the techniques, it's the funny thing about mechanical ventilation is the techniques have been around for hundreds of years. I've got a fantastic book that was written in, I think, 1896. Called Ventilation.
Was that the origin of the word ventilation?
No, I think the interesting thing with that book is it was written before electricity. And so all of the solutions are passive ventilation pollution solutions. And the illustrations in the book are absolutely phenomenal. And it was one of those really odd things of, the way this electronic world of ours is, that sort of sitting at home one night about to watch the news, and this thing popped up on my phone and said, you might be interested in this. And it was one of the Android old books that you can find online. And it just popped into my phone, and I started looking through it. And I was absolutely amazed. There is a print version of it, but they eliminated all of the illustrations. They just scanned the words on it. Huh. And so you have to look at it electronically to see the illustrations.
That's funny. That's like in the music. When I went to music school, there's this jazz book called The Real Book, which is this underground pirated copy of a bunch of, jazz tunes that is totally illegal. It's all copied. It sounds like that kind of a thing, but for building science geeks.
Yeah, well, the old buildings, when they had the transoms, to allow ventilation to flow, and all of those mystery stories with people peeking in over the transom to listen in on what was going on. And there were buildings in England that they had young boys who would crawl through the ducting to adjust the dampers in different seasons because the ducts were big enough for small people to get through.
Wow.
But they were all passively ventilated, which is really quite remarkable.
Do you feel like there's a place for passive ventilation that we're not taking advantage of today?
Well, there's an old saying in the energy business that back when we were doing the solar stuff originally, that passive people lived in active solar houses and active people lived in passive solar houses. And so that you had to, if you do passive ventilation, which can be done, the Europeans do a fair amount of it, but there has to be a fair amount of occupant involvement to adjust dampers and airflows. And one of the reasons it's difficult in the U.S. is because of our lot sizes. The lot sizes aren't big enough to allow the air to flow adequately through the buildings. So it's much more suitable, I guess, maybe out in places where they have big lots and things.
So by that logic, they would never be able to use passive ventilation strategies in Japan, for example, where they've got a population density that's a lot higher.
Yeah, that's an interesting question. That's, by that logic, absolutely, that's true.
Interesting. Do you see an evolution in ventilation strategies around the world? Do you work internationally?
Other parts of the country are considerably ahead of the U.S. as far as ventilation strategies go. Also much higher ventilation rates in places like Europe and Japan than there are in the U.S. There is a fantastic conference that I'd love to go to next week in Belgium. But there's a great organization over there that has great conferences. But yeah, I mean, I think some of the French central ventilation systems are amazing. The British fans they call bad indoor air quality FUG. And one ventilation company had these badges for the FUG fighters.
Nice.
Which was very strange.
Now, I had Hank Rutkowski on the show, and he was talking about this. We're all very extreme in our goals. We want the envelope to be super, super tight, but then we need to introduce ventilation, and of course that increases the load. So then we need to capture some of that, and we got the energy recovery. Where do you see the middle ground where we can just do a really good job and then move on to other things that need attention, like, I mean, to be extreme, like the education system and healthcare and things like that? How much should we worry about these buildings, really?
How much should we worry about these buildings? Well, I mean, I suppose, that would sort of be like, okay, stop breathing, and see how long you last. I mean, one of the problems with buildings is that the natural infiltration rates vary with the weather. And so to rely on natural ventilation, leakage, if your house, for example, meets the basic ASHRAE ventilation rate of 0.35 air changes per hour over the course of the year, that means half the time it's underventilated and half the time it's overventilated. And on average, it's okay. So if we want to breathe on average, then that would be okay. But it seems to me that just like all the rest of this stuff, that as a house, as a system, why would you want to stop putting in mechanical ventilation? I mean, I don't care. You can make one system for very tight houses and one system for moderately tight houses or something. But, I think, who was it that said to me, I think it was John Krieger about a month ago, let's just put a 50 CFM fan in every house and just be done with it. It's like, well, it's probably close to right. I mean, I don't think you need to do all of the math and the fiddling and the energy. When you calculate the math out, the conditioned air cost in a building with ventilation, conditioned air cost for a fan works out to be about $1.25 per CFM anywhere in the country.
Per year?
Per year.
Wow.
So if you have a 50 CFM fan, you're talking about, what, $65, $70 ventilation cost. And your electric cost at these new fans the electric load is about the same as the transformer in a doorbell. And how many people remove the power from their doorbells when they're not using
Well, if you really want to be energy efficient. That's interesting. So you heard it here when you're listening to this show that the top expert on ventilation in the world said that you don't actually have to do the math calculations. So you can refer. Now, are you talking about referring to like a table that tells you if it's this many square feet with this many people in it, then this is the CFM?
Well, I mean, basically looking at the ASHRAE 2010 standard.
So wait, you don't want them to do math because that's hard, but you do want them to actually open the standard and read that.
You can just look at the table. You can just look at the table, and you look at number of square feet, number of bedrooms, and it tells you the CFM. And you really don't have to do all the rest of it.
Cool.
Now, if you want to do the math on the formula, you can do that. If you want to do the infiltration credit, you can do that. If you want to do the existing building Appendix A stuff, you can do that. But you could just simply look at that number. As long as your local inspector will let that be what you need.
Interesting. That sounds like there's a story behind that.
Well, I keep waiting for the ventilation police to be formed and go out.
Do you think that code officials really will begin to even understand the building science behind why ventilation needs to be installed and that it needs to be tested? Most of the time I get blank stares on that.
Oh, I don't know. I mean, building inspectors are of such varied, and they have their own little fiefdoms and their own interpretations. So, I think you have to learn what your local building inspector is looking for and talk to them. And I think the other interesting thing there is as we demand this stuff, as we demand these systems be tested for installation, it's really the interesting thing. Part of that goes to how Panasonic brought their fans into this industry. In the Pacific Northwest was where they brought their fans in, and basically when they came in with really quiet, energy efficient fans, the other big fan manufacturers said they'll never sell them. They're too expensive. Nobody will buy them. Well, obviously people did, and people then started demanding other manufacturers produce quiet fans. And so the sound level went from a typical bath fan, went from 3 sones down to now where it's about 0.3 sones. And 0.3 sones, anything below, I'm getting old enough so that 1.5 sones is about as quiet as I can hear. But 0.3 sones, you don't even, there's no way you can know that it's even running, which causes other problems. But the industry has moved. People did recognize that if it's too loud, people will turn it off. And so the quietness of the fan was important for people to keep them running and let them go for a long time. So I think that the cool thing about inspectors looking at stuff and testing stuff is that it puts pressure on the industry to make stuff, not only good fans, but good tools to test those fans to make sure the installations work as they're supposed to work. So I think it pushes the industry forward.
Now, I'm sure you've seen some very complicated and sophisticated installations. What kind of things have you seen out there that don't work that you might advise people against using?
I can't think of too many. I really think that the products themselves, the heart of the ventilation product industry in this country is the products are tested by the Home Ventilating Institute, and their test procedures are incredibly good. They have a challenge procedure so that if a manufacturer thinks a competing manufacturer is not living up to their standards, they can challenge them, and if they're right, they have to. The product has to be changed, or if the challenger is wrong, they have to pay for the testing. So it's a good process. The specifications on testing are excellent. So I think the real problem in products not working is on installation. And I think if manufacturers have done anything that's not really on the ball, it's to make it easy. The instructions for installing HRVs and ERVs are not really where they should be. I think they should not be hooked up to HVAC systems most of the time.
Can you explain why?
Most of the time, it's first of all, the HRVs and ERVs are designed. They're tested in a balanced condition, and so their efficiency ratings are the efficiency that means the same air in as going out. So if you put them into a house and they're unbalanced, the efficiency of the product can actually improve, but the efficiency of the house changes. And so you may inadvertently have the house operating under positive pressure or negative pressure when you don't intend that to be the case. And so that's why they have to be balanced. So if you hook them up to an HVAC system, particularly if both supply and return are connected, I don't know how you balance it. It's...
You make me feel so happy just now because I've been asking that same question and I am not the world's foremost ventilation expert. So essentially what you're describing is you have the supply on the ventilation plugged into the return plenum, which is a negative, it's a suction area basically where the fan for the air handler is sucking on that. And you have the return, which is where the HRV would be sucking out of the return, which is probably sucking harder than... how does that work? And apparently this does work, but how?
Well, I don't think it works. I mean, basically especially unless the air handler is running all the time that the HRV is running. And think about that for a second, okay? Your HRV fan motor is what, 40 to 80 watts. Your blower motor in your air handler is what, 500 watts? Where's the efficiency here? I mean, if you're trying to save money or energy, that doesn't make a whole lot of sense to me, just from that standpoint. But if the two of them are on the same side, well, if you got to hook them up to the ducting, then take the exhaust from the bathrooms to the HRV and put the supply into the return, but not both. Mm-hmm. And even that way, how do you know how do you balance it? Because when the air handler blower is running, obviously it's pulling through the HRV differently. Mm-hmm. It's like a leak on the return side.
When you are advising people and you train people all over the country, are you pushing them to do a fully separately ducted system with a heat recovery system on it? Or how much time do you spend playing the kind of reasonable card of, we can do exhaust-only ventilation with just a bath fan, but really I want you to do this? I mean, how do you play that kind of middle ground?
I get in trouble all the time. I think, frankly, that a fully ducted HRV or ERV system, well-designed, well-installed, balanced, is the state of the art. That's the best way to go. But if you're going to cut corners on that, what are you actually gaining by putting in the HRV or ERV and spending that extra money? There has been a series, and I've got some great documentation on this, of the fact that if you're doing an exhaust-only ventilation system, you are offsetting the natural leakage from the building. So you're pulling the pressure plane up, and what was, let's say, a 50 CFM fan, the amount of air in 1 CFM in equals 1 CFM out. So if the exhaust fan is mechanically blowing out 50 CFM, then some of the air that would have leaked out naturally is offset by that process. And the math shows that it's about 50%. So if you're calculating the air that needs to be conditioned with an exhaust-only system, it works out to be about 50% of the flow. So, in fact, years ago in Massachusetts, they gave exhaust-only ventilation systems a 50% heat recovery credit because of the way it offset the natural leakage in the building. Now, if you do the math, a lot of the standard HRVs and ERVs are running in the 60, 65, maybe 70% recovery credit. So your energy recovery
is that real?
That's
that 50%?
real.
I mean, is it actually scientifically based, or is it?
Yeah, it's there was a wonderful guy in the Pacific Northwest who unfortunately died in the last year or so, called Larry Palmiter, and Larry did all this incredible stuff. And the Energy Conservatory has a fantastic demonstrating website called CStack. And with CStack, you can change the natural draft between the inside and the outside of the house and see where the pressure plane moves up and down the house. Throw in an exhaust fan and watch the pressure plane move up and move down. And it's a fantastic teaching tool. They have it set up for a very leaky house, a moderately leaky house, and a tight house. And it's a great way to show the way that works.
Okay. Now, if you're listening to this and your head is spinning from what Paul just explained, you're not alone. I'm that way too. Rewind first and listen to what he said again. And if you need more explanation, definitely go get his book. It's the Residential Ventilation Handbook. Now, what are you excited about in the future of ventilation? I mean, when you say the state of the art, are we just have we reached it and that's where we're going to stick as long as every home in America at some point then gets a fully separately ducted HRV or ERV?
Well, I don't think that's really going to occur. But I think, if houses have good bath fans, they have the performance of the fans are tested. I think that in a lot of cases, it's a simple matter of putting in decent ductwork. Smooth ductwork is about 3 times more effective at moving air than flexible ductwork. There's a great table in the ASHRAE standard. It's just spectacular how the variations in those things. Good hoods. Most of the hoods that you get in the big box stores are 4-inch hoods. All the hoods that I sell on my website, I've done equivalent length testing on, so you can actually calculate the static pressure of the hood.
Now, when you say hood, are you talking about the vent terminal on the outside of the house?
Termination fitting.
Okay.
That's right, yeah. I mean, most of them, if you think of the air, when I teach my classes about air, I said, think of yourself as an air molecule. And if you think about people moving into a stadium, for example, when they're standing outside waiting to come in, then they crowd through that little opening and they move very slowly as they go through that opening, and then they fan out as they get on the inside, and as they move around corners, going up the stairs to their seats, they have to squeeze together and slow down. Having those ducts and things be smoother and straighter and a better hood at the end, the termination fitting, some of them are very sharp, and the air has to make a 90-degree turn and push open the door at the same time. And so the flow rate drops significantly at that point. So
some of the air molecules get trampled on the way
that's
out.
Right. They do, and they're they don't like going around those corners. That's what Thule said. Air is like crooked rivers, crooked people, teenagers, and cheap labor. It always seeks the path of least resistance.
Now, with these fully ducted, separate heat recovery ventilation or energy recovery ventilation systems, some of my clients have opted for, and I don't know what I think about this yet. I think that I'm opting against what I'm suggesting, but they talk about just having the exhausts taken out of the bathrooms and having the supply go into the bedrooms and getting rid of the bath exhaust fans, because our ventilation system will be exhausting from the bathrooms. But in a lot of cases, we're talking about a house would need 60 CFM. That's, if there's 3 bathrooms, 20 CFM per bathroom. That does not meet ASHRAE. So how do you, well, for if they've got my kind of clients have steam showers in their bathrooms, of course, and things like that. So 20 CFM, to me, that sounds dangerous, rather than having the point exhaust there as well for backup and having the ventilation system. What would you advise those kind of clients?
Well, as far as ASHRAE goes, 20 CFM continuous from a bathroom is okay. 50 CFM intermittent is okay.
And does ASHRAE take into account the fact that people are doing crazy stuff in their bathrooms?
It doesn't. And in fact, it says that even if you do all this, you might not achieve satisfactory levels of indoor air quality. Because if you have grandpa in the basement smoking cigars, there ain't nothing in the standard that talks about it. Or if you're steam showers or, any of those things. No, it's just it's a minimum ventilation rate. Now, from what you're saying there, yeah, if I'm going to have a steam shower in there, I would, a couple of reasons. One is, for having a spot ventilation system that moves more air more quickly, it's a good idea to take it out at the source. One of the issues that's coming up now are what are the pollutants that we're dealing with, and it's turning out to be there are things like the NOx, the nitrogen oxides, and things that are worse for you in the air than the CO levels and things that we're getting out of these unvented gas fireplaces and stuff. But it's also one of the top pollutants are the very, very small particles, the PM 2.5 particles. And so, without a mechanical ventilation system taking that stuff out, you're going to have problems inside the house. But as far as, I recommend to people, unless they're going to do, steam showers and things in the bathrooms, probably the 20 CFM and maybe, a boost of some kind is not a bad thought. But the thing is, having it run long enough, I have a graph that I showed today in the presentation that I did a fan system that turned on for 20 minutes every hour, 20 minutes on, 40 minutes off. And it's a wonderful curve on the humidity in the bathroom where the showers happen. Well, the first thing I liked about it is that, not being an engineer, relative humidity drops when the temperature goes up, and on the graph, the relative humidity goes along, and then the heat turns on in the house, and you can see that relative humidity drop. And I was, yeah, this is cool. That's the way it's supposed to happen. And then a couple of showers, and then over the course of the day, the fan turns on for 20 minutes, drops the humidity, and then it gradually builds up for 40 minutes, and it drops the humidity, and it goes up for 40 minutes, and drops the humidity. And it takes maybe almost 6 hours before the humidity in the bathroom from those 2 showers gets back to where it was before it started.
And are you saying that that's a good thing, or is that
No, I'm just
long
saying
enough
that bath fans are not ever run long enough to actually dissipate the humidity that's in the bathroom.
Yeah.
So putting in a boost is a good idea, but
it's always got to be complicated.
There's always got to be a but. And on that, the other thing I did was I looked at an occupancy sensor in a bathroom and no fan in the bathroom, and the 2 graphs were identical. So if you're going to use an occupancy sensor in order to you turn the fan on with the light and turn it off when you leave, it's like having no fan at all.
Wow. All right. Now, you mentioned that you are not an engineer. What is your background?
My background is in creative writing. I have written 3 novels that are in my drawer and not published. But that was going to be my career, was writing novels.
Is it strange to have had a published technical reference manual and not your novels?
Yeah, it's very strange. It's very strange. But just to give you a little background, if you don't mind, it's when I got out of school, I went to teach in Labrador in a one-room school in a town that was incredibly adapted to the environment that it was in. The school I taught in had south-facing glass in the schoolroom, and the whole town was built under the shelter of a cliff, and it was well inland. And the way they had the town laid out, the wind would blow through the town. There were no roads, but the wind would blow through the town and between the wood piles and the houses and sweep the snow on the paths where people walked. And so there was never any snow that you had to trudge through because it was all blown off to the sides just by the wind patterns through the town. And my school, although it was south-facing glass, was single glazed, and the temperature was 60 below zero and 120 with the wind chill at times. And so it was quite cold.
Yeah.
And so I had this wood stove in the schoolroom, and it meant that I had to have students constantly getting up, feeding wood into this wood stove to keep the house warm or the school warm. And so I thought, well, I'll put an oil burner in here. And I didn't know a BTU from a cork in a bottle. I mean, I had no knowledge of this. And there was no internet, of course, in those days. But I had this huge encyclopedia, and I pulled out the encyclopedia and looked up BTU and tried to figure out what the heat load was in this school and what size oil burner I would need to put in here to keep the school warm. And I ended up putting in this massive oil burner.
Wow. So you did a heat load calculation with an encyclopedia.
Yeah, it was pretty crude, but it gave me a real sense of what BTUs were and how all of that went together. And it also was a wonderful way of teaching, learning how to teach, because, I really learned how do you teach 8 grades, all subjects simultaneously in one room by yourself, including Canadian history and Labrador history. And so you have to teach them how to read. You have to teach them math. You can't say to the little ones, here, read this while I work on that, because they don't know how to read. And my 3rd graders, when I got there, didn't know how to read. And so I was very lucky. I knew a guy in England who had invented a teaching alphabet that was absolutely fabulous. And I'm sorry that it's gone, but I had my third grade readers reading at a fifth grade level by the time I left, and it was absolutely an amazing experience.
So how did you then get into building performance?
So I went from there back to living in New York City, writing novels, and then I decided I needed to know about electronics for a plot line for a book. I thought it would be really cool to do a home correspondence course. I thought, this is an interesting thing. So I took a correspondence course in electronics and entertainment electronics and fixing television sets and things. And then moved to Boston and started working for the Advent Corporation in Boston, building their big projection TV sets. I went from there to working in a company on Cape Cod that did underwater acoustic systems for positioning oil rigs, and I was their quality control department, did all their photography, wrote their technical manuals, and did all the incoming QC on various electronic components that came into it. And I was living in a very old, drafty house with a British wife who didn't want to turn the heat on. And then the oil embargo came along, and I said, I'm going to get warm. And I got this fantastic book by a guy whose first name, I think his last name is Murphy. And he wrote it in 1973, and it had an infrared picture of a house on the cover, and it's absolutely awesome book. And I was reading that and going, this is cool. I could do this. This is cool. I could do this.
And you can make your house warm.
And it had these tables where you could figure out the R values and do the heat load calculations and figure out how many gallons of oil it would take to heat your house. And I just found an old book last week, in fact, from a guy that gave me proof to me that had the costs of heating your house at different efficiencies for oil burners. And it started out at 80 cents, and I think it went up to like $1.90 or something per gallon.
Wow, awesome.
But, it's pretty amazing.
Yeah.
So that's how I got back to energy efficiency.
Excellent. And so now, teaching people, what is your main message if you have like one thing that you want everybody to take away about ventilation?
Well, I think one of the things that I really like, Corbett, these days is that I'm not doing just ventilation. I'm doing all of it. I do build ventilation because, it's a nice niche to be in, but I think it's really more fun to know every door I open, there's so much more to learn about, furnaces and wall structures and, how windows get installed. And everything has its own incredible volume of information. And I think, coming to these conferences and things, you get these people who are specialists, but they're also generalists. Somebody like, Joe Nagin, he knows a ton about so many things, And I think one of the other things that just sort of sideline, one of the things I really love about this industry is that most of the people in it are absolutely wonderful people. They're nice, they're excited, they've drunk the Kool-Aid, as they say, and they want everybody to experience this stuff. So it's fascinating.
Paul, thank you so much for being on the show.
You're welcome. My pleasure.
Paul Raymer is the Chief Investigator with Heyoka Solutions and also the author of the Residential Ventilation Handbook. You've been listening to the Building Performance Podcast from Green Dream Group in Chicago. I'm Corbett Lunsford. Tune in next time.